Welcome back to the Deep Dive. I want to start today with something weird that happened to me just before we started recording.
Oh, yeah.
I was sitting at the table, getting my notes together, and I have my ceramic coffee mug on one side and my stainless steel water bottle on the other. They've both been sitting here for hours.
So they've settled into the room. They're at room temperature.
Right. Same room, same air conditioning.
Yeah.
But when I rested my arm against the cushion of my chair, it felt fine. Normal. Maybe even cozy.
Okay.
Then I grabbed a metal water bottle, and it felt like a block of ice. And it bothered me. I mean, if they're both sitting in the same room, shouldn't they be the same temperature?
Logically, yes. And, physically, you're correct. They're in what we call thermodynamic equilibrium. Both that cushion and the metal bottle are likely exactly, 22 degrees Celsius, whatever you have the thermostat set to?
But my hand is screaming that the metal is colder.
Eh.
Is my nervous system playing tricks on me?
It's not a trick, but it is a misunderstanding of what your skin actually does. We tend to think of our skin as a thermometer, but it's really not.
It's not. Then what is it?
Your skin is actually a flow meter. It measures the rate of heat transfer.
Okay, wait. So I'm not feeling cold. I'm feeling speed.
In a sense, yeah. Your hand is warmer than the objects on the table. When you touch the cushion, it's lazy. It doesn't accept heat from your hand very quickly.
Right.
But the metal, it's greedy. It just sucks the thermal energy out of your hand at a tremendous speed. That rapid exit of energy is the signal your brain interprets as cold.
So the metal is basically a high-speed highway for heat leaving my body, and the cushion is like a little dirt road.
That is a fantastic way to visualize it. And that, right there, brings us to the core mission of this deep dive. We aren't just talking about temperature, we're looking at the mechanism of movement.
How thermal energy gets from point A to point B. Which brings up a distinction I saw in the research. I always use thermodynamics and heat transfer kind of interchangeably.
Yeah.
But they aren't the same thing, are they?
Not at all. They're related, like siblings maybe, but they have very different jobs. Think of thermodynamics as the big boss. It only looks at the big picture.
The before and after.
Right. It tells you, if I burn this much fuel, I get this much energy, or this coffee will eventually cool down to room temperature. The boss knows the outcome.
But the boss doesn't care how long it takes.
The boss has no concept of time. None. Heat transfer, though, is the project manager. It is obsessed with the schedule. It's asking, how fast is the heat moving? Is it taking 10 minutes or is it going to take 10 hours?
So thermodynamics says the coffee will get cold, and heat transfer says it'll take 15 minutes because you didn't put a lid on it.
That sums it up perfectly, and that project manager heat transfer operates under one absolute unbreakable rule.
Which is?
Heat always, always flows from a higher temperature to a lower temperature.
It's a downhill run.
Always downhill, unless you put in extra work to force it back up, which is what refrigerators do. Nature wants to balance things out. Hot goes to cold until everything is equal.
So we know it moves, but how it moves is where things get really interesting. The sources break this down into the holy trinity of heat transfer. 3 modes: conduction, convection, and radiation.
And you probably experience all 3 every single time you cook dinner.
Let's start with the first one, conduction. This is what was happening with my metal water bottle, right?
Exactly. Conduction is heat transfer through a stationary medium, usually a solid. It's a contact sport.
Stationary medium sounds a bit dry. If I can zoom in with a super microscope, what's actually happening inside the metal?
Okay, so imagine the atoms inside that metal. They're all locked in a grid, like people standing in their spots in a crowded stadium. They can't leave their seats.
Got it.
When you heat one side of the metal, those atoms start vibrating like crazy. They get excited.
So they start dancing.
A very aggressive dance, yeah. They start bumping into their neighbors, the atoms next to them. That bump transfers energy. Then the neighbor starts vibrating and bumps the next person, and so on.
One of the articles used a bucket brigade analogy.
It's the classic analogy because it just works so well. Imagine a line of firefighters passing buckets of water. The firefighters aren't running anywhere. They are standing still.
But the water.
The energy moves rapidly down the line from hand to hand.
And the speed at which they pass that bucket depends on the material.
Crucially, yes. This is a property called thermal conductivity, and engineers use the letter Tauler for it.
I saw some of these numbers. Aluminum has a Collar value of around 205.
Which is really high. Aluminum atoms are excellent at passing that bucket. Now compare that to something like glass, which is around 1.1, or even wool, which is way down at like 0.07.
Whoa, that is a massive difference. So aluminum is thousands of times faster at moving heat than wool.
which is exactly why we wrap ourselves in wool and not aluminum foil when we go out in the snow. Wool is an insulator. It refuses to pass the bucket. It traps your body heat right next to your skin.
So is there a way to calculate how fast this flow happens? Or is it just fast or slow?
Oh yeah, there's a specific mathematical law for it, figured out by Joseph Fourier way back in 1822.
Fourier's law.
And he realized that the rate of flow depends on two main things. First, the material's resistance, that dollar value we just talked about, and second, the driving force.
The driving force being the temperature difference.
Exactly. Imagine water flowing down a hill. The steeper the hill, the faster the water rushes down, right?
Sure.
In heat transfer, the bigger the temperature difference between the hot side and the cold side, the faster that heat flows. If you have boiling water on one side of a thin wall and ice water on the other, heat is going to just sprint across that barrier.
So conduction is the bucket brigade.
Yeah.
Atoms bumping atoms. But that only works for solids. What happens when we talk about liquids or gases, things that can actually flow?
That brings us to the second member of the Trinity, convection.
I feel like this is the one people confuse with conduction the most.
It happens all the time, but the key difference is just one word: movement. In conduction, the particles stay put. In convection, the particles themselves actually move from place to place.
So you're using the fire analogy.
Instead of passing the bucket down the line, the fighter grabs the bucket and literally sprints toward the fire. The material itself is transporting the energy.
Okay, that's a really clear visual. And the sources mentioned there are two flavors of this, natural and forced. Natural convection is what happens in a kettle, right?
Or in the very room you're sitting in. Hot air is less dense than cold air. So the hot air rises, it displaces the cold air, which then sinks. That creates a natural loop, a cycle.
It's buoyancy.
It is. That's why your feet are usually colder than your head in a drafty room. The cold air is pooling at the floor.
And forced convection is, well, cheating.
It's just impatience. We don't want to wait for buoyancy to do the work. So we use a fan or a pump or even just the wind.
Like with a spoonful of hot soup.
Perfect example. If you just hold it there, natural convection will eventually cool it. Hot air rises off the soup, cold air comes in. But if you're hungry,
I blow on it.
you force air across the surface. This actually relates to Sir Isaac Newton's law of cooling. He figured out that the cooling rate depends heavily on how fast that fluid is moving over the object.
This brings me to my favorite term from the research, the boundary layer. It sounds like something from a sci-fi shield generator.
It kind of acts like one. This is a really important concept. See, even if you have a fan blowing right next to the surface of that soup at a microscopic level, the air is stuck. It's not moving at all.
It's clinging to the surface.
Friction holds it there. It creates the sticky blanket of stagnant air. So the heat has to first crawl through that blanket slowly using conduction before it can get swept away by the fast-moving air.
So when I blow on the soup, what am I actually doing to that blanket?
You are stripping it away. You're thinning that boundary layer down to almost nothing so the heat can just escape instantly.
That is surprisingly violent for eating dinner. We're ripping the air blanket off our food.
Physics is often violent on the micro scale.
Okay, so we have conduction atoms bumping, we have convection atoms flowing. Both of those require matter. They need a medium. But that creates a huge problem.
The space problem.
Right. The sun is 93 million miles away. Between us and the sun is a vacuum. There's no air, no water, no long line of firefighters passing buckets. So how do we feel the heat?
This is radiation, the third mode. And it's the only form of heat transfer that doesn't need a medium at all. It travels as electromagnetic waves, photons.
Like light.
It is light, just not always the kind of light we can see. It travels at the speed of light, zipping through the emptiness of space until it slams into something.
And the sources say everything does this, not just the sun.
Everything. If it has a temperature above absolute zero, it is emitting radiation. You, this microphone, your cat, you are all glowing right now in the infrared spectrum.
I'm broadcasting heat.
Constantly. And objects are absorbing it too. There was a great example in the reading about a radiometer. You know, it looks like a light bulb with a little spinning windmill inside.
Oh, I've seen those in science museums. One side of the vanes is black, the other is shiny and silver. You put it in the sun and it just starts spinning.
And it spins because of how those surfaces handle radiation. The black side is what we'd call a good absorber. It just drinks in the light and gets really hot. The silver side reflects most of it and stays cool.
So the gas molecules inside the bulb hit that hot black side and they get a bigger kick.
Exactly. They bounce off much harder, and that pushes the vane. It's a little heat engine powered by light.
This connects to that black body concept, doesn't it?
Right. A black body is a physics ideal. an object that absorbs 100% of the radiation that hits it and then emits it perfectly. In the real world, things like matte black paint or asphalt get pretty close.
Which is why walking on a paved road in July feels like walking on a grill. There was a math point here that I think is crucial. The Stefan Boltzmann law. It mentioned the fourth power.
This is huge. It means radiation is incredibly sensitive to temperature. If you double the temperature of an object, the amount of radiation it blasts out doesn't just double.
No.
It goes up by a factor of 16.
Whoa. So a small increase in heat leads to a massive, massive jump in radiation.
It's exponential. At room temperature, radiation is pretty weak, but as soon as things get red hot, radiation becomes the dominant beast. It completely takes over.
Okay, so we've got the Trinity: conduction, convection, radiation. But let's see what happens when we actually try to use these rules to build stuff. The so what factor.
Engineering is basically just managing these three flows. Either you want to stop them or you want to encourage them.
Let's take the lunchbox challenge. I want to keep my sandwich cold.
So you want to stop the flow. You choose materials with low conductivity like foam or plastic to stop conduction. You make it airtight to stop convection currents. And yeah, maybe you line it with foil to reflect the radiation.
Okay, that's pretty straightforward. But let's look at the Mars challenge. This one kind of blew my mind. We need to send a container to Mars. It's freezing there.
Extremely cold. And the atmosphere is incredibly thin, almost a vacuum.
So my first thought is, okay, pack it with tons of insulation so it doesn't freeze.
And you should. But there's a paradox here that trips a lot of people up. In space or in a vacuum, a container is basically a thermos.
Right, because there's no air to conduct or convect heat away.
Exactly. A vacuum is the ultimate insulator against conduction and convection. But what if your container has electronics inside? Like a computer?
Electronics generate their own heat.
They do. On Earth, a computer uses a fan to blow air over the chip. That's convection. But on a spacecraft, there is no air to blow. You can't use a fan.
So the heat is trapped.
It's trapped. You have a computer generating heat inside a super insulated vacuum bottle. It will cook itself. It will literally melt.
So wait, the problem in deep space isn't just freezing, it's also overheating.
It is a massive, massive problem. Since conduction and convection are off the table, the only way to get rid of that heat is radiation.
Because radiation doesn't need air to travel.
Bingo. So engineers have to build these massive radiators, giant panels designed to just glow in the infrared to shed that waste heat out into the universe. If they get that math wrong, the whole mission could fail.
That completely flips the script. You have to rely on the one mode we usually ignore on Earth.
It really highlights how context just changes all the rules.
Speaking of computers, let's bring it back to Earth. The source used the CPU cooler as the ultimate synthesis of all three modes working together.
It is a beautiful little symphony of heat transfer. Think about the chip in your laptop. It's getting hot.
First step, conduction.
The heat conducts from the silicon chip into the thermal paste and then into the big metal heat sink. That metal needs super high conductivity to pull the heat out fast.
Step 2, convection.
The fan kicks in. It forces air through those metal fins on the heat sink, stripping away that boundary layer we talked about.
And step 3,
radiation. The hot metal fins are also radiating heat out into the computer case. Now, it's the smallest factor here, for sure, but it's still happening. If you lose any one of those, if the paste dries up or the fan dies, the whole system fails.
It's amazing how fragile that balance is.
It keeps our entire digital world running.
Before we wrap up, I want to step back a bit. We talk about this like it's obvious, atoms vibrating, photons flying. But for a long, long time, humanity had this totally wrong.
Oh, completely. For centuries, the smartest people on Earth thought heat was a substance. An invisible fluid they called caloric.
Like an invisible juice that flows around.
Exactly. They thought if a rock was hot, it was because it was swollen with caloric fluid. And if it cooled down, it was because the fluid had poured out.
So what killed that idea?
Friction. And a guy named James Prescott Joule, he did these brilliant experiments where he showed that if you do work like rubbing things together or churning water with a paddle, you create heat.
And since you can keep rubbing sticks together forever and they just keep getting hot,
you can't be squeezing a finite fluid out of them. You'd run out. Joule proved that heat isn't stuff, it's energy, it's motion.
The mechanical equivalent of heat.
And that changed everything. It gave us the laws of thermodynamics we still use today.
So let's recap the toolkit we've built today.
Okay. Number 1, conduction. That's the bucket brigade. Heat moves through solids via direct contact.
2, convection.
The courier. Heat moves because the fluid itself moves.
And 3.
Radiation, the broadcast. Heat moves as waves through empty space.
And we learned that our skin is kind of a liar. It feels the speed of the transfer, not the actual temperature.
Which is a fun fact to drop at dinner parties, for sure.
I want to leave our listener with one final thought that came out of the research on heat pumps. We said the golden rule is that heat flows from hot to cold.
That is the natural order of the universe.
Yeah, but I'm looking at my refrigerator right now.
Mm.
It is actively taking heat from the cold inside and pushing it out into my warm kitchen. It breaks the rule.
Yes. It fights the rule. It doesn't break it. And that's why it needs a motor. That hum you hear from your fridge. That is the sound of electricity doing work to push a boulder up a hill against gravity.
We are literally paying the electric company to reverse the laws of physics in our own homes.
Every single day. It really makes you appreciate just how stubborn nature actually is.
So here is your homework for the week. Look around your house. Find the things that feel unnaturally cold, like that metal table leg, and the things that feel warm. Think about the invisible boundary layers of air clinging to your soup. Once you start seeing the flow of heat, you really can't unsee it.
It does add a whole new layer to the world.
Thanks for listening to The Deep Dive. Keep checking those thermal conductivities.
See you next time.